All right, lesson 4.2, ready section is to find the zeros of each polynomial. And in the case of the first couple here, we're already in a factored form. So what you want to do is set each factor equal to 0. So on number 1, if we set x plus 4 equal to 0, we're going to get x equals negative 4. If we set x minus 2 equal to 0, we're going to get x equals 2. If we set x minus 7 equals 0, we're going to get x equals 7. Okay, on number 2, same approach. 2x minus 6 equals 0 will give me x equals 3. 8x minus 1 equals 0 will give me 1/8. You add 1 and divide by 8. And the last root, x minus 5 equals 0, will give me 5. So what I'm doing here is I'm taking each factor and setting it equal to 0. I add 1 to each side and divide by 8. All right, so the next one, 9x plus 3 is equal to 0, is going to give me, when I reduce it, negative 1/3. X squared minus 9, that's not in a factored form. I can factor it as x plus 3 times x minus 3, and then get 3 and negative 3. Now, number 4 is a little tricky because it's not factorable over the set of real numbers. But if you set that equal to 0, you get x squared equals 25. So my roots are going to be positive and negative 5i. The other way to approach that one is that you can't force factor it as x plus 5i times x minus 5i. If you expand the numbers that you can factor over to the complex number system. All right, finding the domain. You cannot divide by 0, so the domain on number 5 is all real numbers except x equals 4, 2, and 7. Now, that's writing the domain in sort of the negative by saying it's all real numbers not equal to 4, 2, and 7. On a number line, you could argue that's negative infinity to a 2, pop out the 2, and then 2 to 4, pop out the 4, and then 4 to 7, pop out the 7, so that if I shade in green here, all these intervals, like negative infinity to 2, that open interval, united with 2 to 4, united with 4 to 7, united with 7 to positive infinity. You may see answers like that in a key. I think this is more precise and concise. So on the next one, the domain will be all real numbers except, I guess back here, if I do except right here, oops, sorry. If I do except here, then this should be x except x equals, or not equals. That would be a double negative. So here would be except x equals the root of this guy, which is 3, the root of that guy, which is 1/8, the root of this guy, which is 5. So it looks like we're correlating these answers to the answers in the previous section. So on number 7, that's going to relate back to number 3. So the domain is going to be all reals except the roots we got in number 3, which were x equals negative 1/3, 3, and negative 3. Okay, now notice they don't do this one down in here because x squared plus 25 can never equal 0. So if that one were there, the domain would be all reals. Ooh, it is here, my bad. The domain here is all reals because this guy here can never equal 0. All right, bear with me on the graphing because it's a little tedious here to, it's not tedious, but it's a little hard to get nice graphs here. I would suggest maybe checking with Desmos just to make sure, but 4 over x, the vertical asymptote is going to be what? The vertical asymptote is what makes the denominator equal to 0. So x equals 0. And the horizontal asymptote is the limit of 4 over x as x goes to infinity, which would be y equals 0. The domain is all real numbers except x equals 0. And the range is going to be, I'm going to do this one as, the range, I guess, is all real values except y is equal to 0. Okay, so the graph here, again, I say bear with me here. I'm going to bring my x, y axis in. You know what I'm going to do here? I'm going to do this off the grid because I think it's easier for me. So it's going to come down like that, and over here like that. So if I highlight my horizontal asymptote in red, there it is right there. And if I highlight my vertical asymptote in green, it's the y-axis there. And the argument is that as I go towards infinity over this end, and negative infinity on that end, I head for zero, the asymptote. And then I get close to zero, there's 4 over a very small number that's positive. It's going to be going towards positive infinity up here. And then the opposite is true going that way. All right, so the next one, number 3, my vertical asymptote is again x equals 0. I'm getting that from this guy right here. My horizontal asymptote is y equals 2. I'm getting that from here. My domain is going to be what? All reals not equal to 0, because I got a vertical asymptote of 0, and my range is going to be, I can do this as y not equal to 2. Because that up here is y cannot equal to 0. Okay, so if I go over here to my graph, my my horizontal asymptote is y equals 2 going that way. And so my graph is coming similar to the one we just did. Sort of like that. So it doesn't ask you, you could, obviously there's an x-intercept here. So that's that one. All right, the next one, the vertical asymptote is at what? X is equal to 3. Getting that from x minus 3. The horizontal asymptote is y equals 0. The domain is all real numbers not equal to 3. And the range is all real numbers not equal to 0. Okay, so again, if I go off the grid, I find it easier. The vertical asymptote is at 1, 2, 3. So that's right there. My horizontal asymptote is y equals 0. That's in the red right there. And then my graph is going to go which way? I got a negative sign in front here. Notice that. So it actually goes up on this side and down on that side. The way I handle this is I pick a value just to the left and right of the vertical asymptote and plug it into the function to see if it's positive or negative. If it's positive, it goes up on that side of the asymptote. If it's negative, it goes down. All right, number 12, my vertical asymptote is x equals negative 5. My horizontal asymptote is y equals negative 4. I'm getting that from here. My domain is going to be all real numbers not equal to negative 5. And my range is going to be all real numbers not equal to negative 4. So I come over here, my vertical asymptote is at negative 5. So 1, 2, 3, 4, 5. There's my vertical asymptote. My horizontal asymptote is at negative 4. 1, 2, 3, 4, we'll call it. Let's go down in here. And I have no negative sign here, so my graph is coming up the asymptote on that side, down the asymptote on this side. Again, test a test value a little bit to the left and right of the asymptote. All right, 13, based on what we just did there, we should be noticed that the vertical asymptote comes from the h position. So we can go with f at x, let's say 1 over x minus negative 15, which becomes plus 15. And then notice that the k is giving us the horizontal asymptote, so that's minus 6. This could be other than a 1 right here. All right, now this is sort of review from previous sections, so this is going to be a lot of synthetic division. If I take the number negative 1, the root, negative 1, and then the coefficients from the polynomial, 1, -1, -17, and -15, do a synthetic division, 1, -1, negative 2, 2, negative 15, 15, and 0. This tells me the quotient of the x plus 1 divided into the f at x polynomial. So that leaves me a polynomial x squared minus 2x minus 15, which factors as x minus 5 times x plus 2. So my roots are negative 1, 5, and negative 2. Same process on the next one. Change colors just to distinguish it. I put a 1 with a what? 1, negative 3, negative 61, 63, 1, 1, negative 2, negative 2, negative 63, positive 63, 0. Whenever this is a root, the last number in syntectic division is the remainder, which is 0. That gives me an x squared minus 2x minus 63, which is x minus 9 times x plus 7. So my other root is 9 and negative 7 along with the given one, which is 1. So these are sort of the sets. You can think of it as a set of the solutions. So let's go red on the next one. 16. I've got this one's a little different. I can do this one by factoring. I'll slide it in underneath here. I can factor out 6x, leave me x squared minus 3x minus 10, which is 6x times x minus 5 times x plus 2. And there are my roots, 0, negative 5, and 2. I don't want to do synthetic division with a 0. Nothing would show up really. All right, back to synthetic division. We take the given root, 8, coefficients 1, negative 14, 57, negative 72. And for this one, we're going to bring down the 1, get an 8, negative 6, negative 48, positive 9, 72, and 0. Arithmetic here is important. Leaves us with x squared minus 6x plus 9. That's a perfect square. It's x minus 3 squared. So I get 8 and a double root of 3. Okay. All right, the last one's a little different in that we've got an imaginary root. We could do synthetic division rather with an imaginary root, but remember that if 2i shows up, positive 2i shows up, then negative 2i has to show up as well. So imaginary numbers show up in conjugate pairs. So that means that one of my factors is x minus 2i, and the other one is x plus 2i. And if I have roots over here, root 1 and root 2, then I have to have factors that match up to those. If I multiply those together, I get x squared plus 4. And now this time I'm going to do long division, the dreaded long division, into the polynomial, because I'm not going to do synthetic division with a quadratic factor. So my divisor is x squared right there. So x squared into x cubed is x. I'll put that over here because that's aligning common like terms rather. So that gives me x cubed plus 4x. Again, aligning like terms. When I subtract, it leaves negative 5x squared minus 20. This is sort of an iterative process. Now I divide the x squared into the negative 5x squared. I get negative 5. And that aligns perfectly. It gives me a remainder of 0. So my other root of x is equal to 5. So I get 2i, negative 2i, and 5. The negative 2i sort of comes for free because irrational roots and imaginary roots appear in conjugate pairs. And conjugate means that if you have something like an a plus a b, you have to have a minus a b. These are monomials, so if one of the roots was 1 plus 2i, the other root would have to be 1 minus 2i. Or if one of the roots was negative root 2, the other one have to be positive root 2. Okay, so that is, oops, that is